have discussed the Hilbert adjoint operator of a bounded linear operator T, of T, which is a bounded linear operator from Hilbert space H to another Hilbert space H2, H1 to H2, and we have introduced the Hilbert adjoint operator T star is an operator from H2 to H1 such that the inner product of Tx by is the same as Xt star by, and this definition, if T is a bounded linear operator, then it is shown that T star will exist is a bounded linear operator and both will have the same norm. This much we have discussed last. Now, with the help of this Hilbert adjoint operator, we can classify the bounded linear operators and we can have it further subclasses for the bounded linear operator that we call it to be a self-adjoint operator, unitary operator, normal operator, and so on. So, with the help of this Hilbert adjoint, we can define the following for the bounded. The self-adjoint of a bounded linear operator T from the Hilbert space H to Hilbert space H on a Hilbert space H is said to be self-adjoint or Hermitian if T star equal to T. Okay, that is Hilbert adjoint operator of T coincide with the original operator T, then we say such an operator is a Hermitian operator or self-adjoint operator. Then the operator T is said to be unitary if T is bijective. Bijective means it is 1 1 and on 2. So, injective and surjective both. So, bijective and T star should coincide with T inverse. Then it is said to be normal if T star T coincide with T star. Okay, and this we have seen that every self-adjoint operator is normal operator, unitary operator is normal. So, as a remark, we have seen in fact that self-adjoint operators and unitary operators are normal operator, are normal, is it not? Just by definition, if you just apply the definition, you get the condition of the normal operator satisfied. But the converse is not true. What normal operators need not be self-adjoint or unitary, and this also we have seen. For example, we have taken the operator T, which is 2ii. I is the identity operator, and this we have seen that this operator T, when we find the Hilbert adjoint operator, this is the star means 2ii, and the corresponding inverse will be minus 1 upon 2ii minus I over 2I, sorry, this inverse operator will be, product of this should be 1. So, this will be minus 1 upon 2 I up, is it not? Then only you are getting I square is minus 1 and half of cancel and we get. So, T star and T inverse this, and it is easy to verify that this operator is a normal operator, but not neither a self adjoint nor the unitary operator. Okay. So, this we, so up to here we can see. Now, as we know that an operator, a linear operator defined on a finite dimensional space can always be represented by means of the matrix, and if we fix up the basis, the order of the basis, then corresponding operator will be unique in nature. Okay. So, if suppose be an operator which is a bounded linear operator on a finite dimension, in fact every linear operator on a finite dimensional space will be a bounded linear operator, is it not? If T is a linear operator on a finite dimensional space x to y, then it must be a bounded linear, because continuity follow, and continuity means boundedness will be there. So, if T is an operator from say one finite dimensional space to the same finite dimensional space, let us say Cn to Cn, then it can be represented by means of the matrix. Hence, the question arises, what will be the corresponding form of the Hilbert adjoint operator of such an operator? Can be expressed the Hilbert adjoint operator of this operator T in terms of the matrix, which may be the conjugate transpose of the previous matrix or something else. Clear? So, we wanted to drive the relation for a Hilbert adjoint operator when T is defined over a finite dimensional Hilbert. So, the relation, you can say relation of T star, okay, in terms of matrix. Clear? Now, suppose T is an operator from Cn to Cn, be a bounded linear operator. Okay. Suppose we have this operator which is a bounded linear. Since Cn is a finite dimensional n dimensional space, so it is finite. So, clearly even if I do not take the bounded, just if I take only linear T, okay, then clearly T is bounded, because Cn is a finite dimensional vector space. So, if an operator defined on finite dimension, it will be a bounded, a linear operator will be bounded. So, it is a bounded linear operator. Let us fix the basis, fix up the basis for Cn. Okay. So, it can be, so T can be represented by means of a matrix, say A. Is it clear? By means of the matrix A. Now, Cn is a n dimensional, the inner product on Cn is defined as inner product of x by equal to what? If x is say xi1, xi2, xin, y is say eta 1, eta 2, eta n, then the inner product basically is defined to be sigma xi I, eta I bar, I is 1 to n, and in fact this is nothing but what? This will be in vector form. If I write, it is the x transpose y bar, is it not? X transpose y bar. This is our way of defining the inner product. So X and Y are there. Therefore, if I take the Tx, so T is so Txy, inner product of this. Clear? Txy will be what? X is replaced X transpose. So Tx will be Tx transpose and then y bar. Is it not? But A B transpose is the B transpose A transpose. So from here we get X transpose T transpose or T is defined by Ax. T is defined by Ax. So I will write this is Ax transpose y bar. Okay. T is because T is a operator on a finite dimension, so it will be represented by the matrix A. So it will be A transpose into y bar. Is this clear or not? So we are getting this one. Let it be 1. Okay. Now again, T star is an operator from Cn to Cn, reverse batch side. So it is also bounded linear operator by definition, and since it is finite dimensional, so T star can be represented by means of a matrix, say V. Okay, by means of a matrix, say V. So it will be T star of X. So what will be this? X Tx by, we know that Tx by is equal to Xt star by. Now Tx by we have already defined a X transpose At by bar, and here this will be what? Transpose of this into T star by conjugate by definition. But X transpose T star by is what? Is the B by conjugate, because T star is defined by a matrix B. So it will be equal to B bar by bar. Okay. So if we compare these two, this implies that B bar comes out to be the A transpose. It means that is the matrix B is coming to be the conjugate of transpose of A. Clear? So what we get it, if T is represented by a matrix A, then corresponding Hilbert adjoint operator is represented by the conjugate transpose of this matrix. Okay. So we conclude, hence, if a basis for Cn is given and a linear operator on Cn is represented by a certain matrix, then its Hilbert adjoint operator T star is represented by the complex conjugate transpose of that matrix. Is it okay? So, this is what we get it, representation of a Hilbert adjoint operator in terms of the matrix. Clear? Previous slide, okay.
Sir, you know that if we fix the basis, then always we can represent with some matrix.
Yes.
But if we take the standard basis, then the vector, any vector and its coordinate vector will be the same. So in that case, directly any vector should be represented, any vector y.
No. When we fix the basis, it means, it does not mean that you are taking the particular basis. No. Your basis, the elements of the basis order is fixed. When you are taking the basis, it means the order of that elements are fixed. So throughout the calculation, you keep that basis itself. So every point x can be represented in terms of that basis, and representation will be unique in that way. Oh, slide is?
Yes, slide is there.
What is your point? Yes. Acha, okay. Okay. So what is there?
My point is if we take the any basis, then the representation is something that the coordinate of y equal to that vector matrix representation and the coordinate of x, coordinate vector. And here we are taking x and y is not coordinate vector as any vector.
No, it's not. X itself is represented. When you say x equal to xi1, xi2, xin, it means x is represented in the form of, say, this is, suppose I take any vector 1 0 0, an element, it will be represented in terms of the basis element. What is this basis element? X is E1, say alpha 1, alpha 2, E2, alpha n, En. When these are fixed, it means when x is given, then these coordinates alpha 1, alpha 2, alpha n cannot take any other value except only one. So it means this xi1 E1, xi2 E2, these are the xin En. This will be the representation of x. So xi1, xi2, xin are fixed, and that's why we are taking in terms of x.
Means here x is also the coordinate vector.
X is the vector or coordinate vector, and because these coordinates are determined because of the basis is fixed.
The
Order is fixed. Okay, so that's why. Clear? So I think it's okay. Now let us see the relation again further. We know in case of the general matrix or in matrix theory, if you remember, this is okay. Now we know in the matrix theory, we say a matrix A is Hermitian if the conjugate transpose of this matrix coincide with A. Is it not? And skew Hermitian with minus sign, if this is minus A, and we say it is a unitary if conjugate transpose of this equal to A inverse, and we say it is normal if A bar transpose equal to A bar transpose A. Is it not? Now what is our definition? If you remember, we have defined the self adjoint operators sheet where it is. Okay, how did you define the self adjoint? This is the way. Here we have defined T star is equal to T. What is T star? T star was coming to be the conjugate, complex conjugate transpose of this matrix. So is it not a T star? And this is T. So we can say a matrix is Hermitian when T star is equal to T. And that is why we have told self adjoint or Hermitian. Clear? Similarly for the unitary we can say. So we can say from here is that a matrix, so we can say matrix are Hermitian Hermitian if the corresponding operator T is self-adjoint. Is it okay? And we say it is unitary if the corresponding operator T is unitary. Okay, and it is normal if the corresponding operator T is normal. Is it okay? So we can relate the theory of matrix with the operators. Clear? Now we have few properties of the self-adjoint operator in the form of result. So first theorem, that is on the self-adjointness. If let T from H to H be a bounded linear operator, on a Hilbert space H, then if T is self-adjoint, then the inner product Txx is real for all x belonging to H. And second is, if H is complex and inner product Txx is real for all x belonging to H, then the operator T is self-adjoint. Okay, operator T is self-adjoint. Solution of proof. What is given is T is a bounded linear operator and T is self-adjoint. So given T star is equal to T. We want this to be real. So consider inner product of Txx conjugate. If I prove the conjugate of this is the inner product itself, then it will be real. Okay. Now this will be equal to inner product x T star x conjugate. Is it not? And this will be equal to T is given to be self-adjoint. So this is the same as x Tx conjugate, because T star is equal to T. Is it okay or not? Now again interchange the order. So when you interchange the order, it is the same as Txx. So this shows the inner product Tx comma x is real. Okay, nothing too much. For the part B, given H is complex, so it means the Hilbert space H should be a complex valued, means field of this scalar should be a complex number. For real it may not be, means may not be true, we cannot get the conclusion. Okay, so H has to be complex here, and Txx is real for all x, then operator T is self-adjoint. So this is given Txx is real. What is given? Inner product Txx is real. It means conjugate of this is the, okay, but this the same as x T star x conjugate is the same as Txx, but this is the same as T star x comma x is Txx. This is true for all x belonging to H. Okay, now from here we can write it, inner product of T star minus Tx comma x is 0 for all x belonging to H. Okay. Now, if Qxx is 0 only when implies Q is 0 only when H is a complex space. Otherwise, in case of the real, you have seen that Qxx is 0 in spite of Q cannot be 0, because if you take the rotation operator, then it can rotate the x through the 90 degree and the inner product comes out to be 0. Clear? But if H is a complex inner product space, then in that case this Qxx is 0 for all x will imply that Q must be 0, that is, this is a 0 operator. So, this shows T is self-adjoint. Is it okay? Otherwise, it cannot. Clear? So, these two. Okay. Now, another property for this composite, the product of the two bounded, the product of two bounded self-adjoint linear operators S and T on a Hilbert space H is self-adjoint if and only if the operators commutes, that is, if ST equal to TS, then the product ST will be self-adjoint, and vice versa, if product ST is self-adjoint, then S and T will commute. Okay. So, what is given is given S star is equal to S, T star is equal to T because of the self-adjoint. Is it not? Both are given to be self-adjoints. Now, what we want is product ST star should be self-adjoint. So, ST star, consider this. Okay. Now, if you remember, yes, when you take the product UV star, it becomes V star U star. So, this will be equal to T star S star. So, start with this. Okay. Then this comes out to this, which is equal to TS. Okay. Now, if we assume that TS equal to ST, then ST star becomes ST. So, if we assume this is equal to ST, this is given TS equal to ST, then it will imply that ST star equal to ST. Is it not? And that will give you the solution that ST is self-adjoint. Is it okay? Now, let us see the converse way. Suppose ST is self-adjoint, then ST must be equal to ST star. ST star means we are getting from here this side. ST star means T star S star, and this is equal to ST, so TS equal to ST, and that will imply ST. Okay. So, vice versa is true. Clear? So, this proves the result. Is it okay or not? So, we can say ST star equal to ST if and only if ST equal to TS. Okay. So, this completes the proof. Now, next result shows the sequence of the self-adjoint operator. means if there are T1, T2, Tn are the sequence of self-adjoint operator, then the limiting point of this limiting operator, whether will it be also a self-adjoint or not. Now, this is given by the next result, that if there are certain conditions on Tn's, then it will, the limit operator will also be a self-adjoint operator. So, what is this result? So, let Tn be a sequence of bounded self-adjoint operators from H to H on a Hilbert space H. On a Hilbert space H. Suppose that Tn converges. Say Tn goes to T, under which? Under the norm of BHS, norm of BHS. This is the norm of BHH, bounded set of all bounded linear operators defined from H to H, and the norm is defined as the supremum norm of Txx over norm x, where x belongs to H. So, Tn converges with, that is, norm of Tn minus T goes to 0, edge, and tends to infinity. That is true. Okay? Where norm is the norm on the space BHS. Is it okay? BHS. Now, what he says is, then the limit operator T is a bounded self-adjoint linear operator on H. Okay. So, what is given is that Tn is a sequence of bounded linear operator on H. Here H is a Hilbert space, and Tn converges to T under the norm of BHS. Then what he says is T will be a bounded self-adjoint linear operator on H. Now, clearly T is bounded. I think it is obvious or not. If sequence Tn be a sequence of bounded linear operator, the limiting operator will also be bounded. Why? Because what is the norm of T? That can be written as T minus Tn plus norm of Tn less than equal to. Now, this goes to 0 and this is bounded, finite, is it not? So, basically this is finite. Okay? Or you can start with norm of Tx, then you can take Tnx minus Tx and goes. Okay? So, that will be bounded, sequence will be bounded. Okay? So, this is nothing. Is it okay? Now, T is bounded. So, what is left is, we have to show that T star is equal to T. T is a bounded self-adjoint operator, T star is equal to T, is it not? That is, instead of this we can show, that is, if I prove that norm of T minus T star is 0, then we can say, because norm of x is 0 means x must be 0. So, T is equal to T. So, instead of showing this, I will prove this, which is easy to prove because the sequences are converging in the norm. So, we will use the norm for this. Is it okay? Fine. So, start with this norm of T minus T star. Add and subtract Tn's. So, this will be less than equal to T minus Tn plus Tn minus Tn star plus Tn star minus T star. Is it okay or not? Clear? Now, this will be written as T minus Tn plus Tn is a self adjoint operators, is it not? Given that Tn be a operator self adjoint, this is given to be self adjoint. So, Tn star is equal to Tn. So, this part will always be 0, and here we can we not write this thing as norm of Tn minus T, that is all. Why? Because of the reason the Tn minus T star norm of this is the same as Tn minus T. Self adjoint operator, they have the same norm, is it not?
Otherwise, Tn minus T will also be an operator.
All be operators. So start when you take. So we are taking this thing means 2 times norm of T minus T. Okay. Now as n tends to which goes to 0, as n tends to infinity. Therefore, norm of T minus T star is less than or equal to 0. But norm cannot be negative. So this implies that T must be equal to T. Okay. So self adjointness proves.
Yes, sir. Can you prove anything like this for the norm? Here we are taking T as a basically the vector.
Where?
Basically, sir, the norm of we find basically the triangular inequality.
That no, it's not, because we have proved established this inequality in case of the operator. How did I prove it? If you remember, T1 plus T2 norm of this. Okay, we have taken supremum norm of T1 plus T2 x, where the supremum is taken over x and norm x equal to 1. Is it correct or not? Now this will be, because T1 T2 are bounded. Okay, so this will be less than or equal to norm of T1x plus norm of T2x. Is it not? And supremum of this and supremum of this. Is it okay? Of now this supremum of this over x belongs to H, where the norm x is 1, where the supremum is taken x, where the norm x equal to 1. So this will be equal to norm T1 and this will be equal to norm of T2, less than or equal. So this shows less than or equal. So basically it behaves as if it is a algebraic inequalities. But
my point is this is okay.
Okay,
But otherwise also we can think that T1 and T2 is an element of BHH. BHH is the vector space.
Yes.
So T1 and T2 will be a vector
Yes,
space.
yes.
So
they can follow the triangular inequality. But every vector space, that does not mean that it will follow the triangular inequality. You have to establish, is it not? You have to establish. Otherwise, the vector spaces are there. Vector space itself requires the triangular inequality, is it not? By the condition, if you go through the vector space definition, it requires the triangular inequality there. Only thing you can say, vector space, if T1, T2 are there, their linear combination are in there. But it does not mean that inequality will follow.
In a vector space, if we can define a norm, then that norm will follow the triangular inequality.
No, norm, but we have to establish, because it's not that every norm, is it not? Sometimes the like our metric space, if I take, say XD is a metric space, and if I define the norm in terms of the D metric, dx by over 1 plus dx by, it does not satisfy that one. Is it not triangular? What is the norm? Norm, if I define in terms of sigma 1 upon 2i and so on, it does not satisfy the triangular inequality. Is it not? Every norm, that will be problems, is not necessary to be there, because norm of alpha x is not there. So that itself is not a norm. If I define that way, triangle will follow, but it will not define the norm. If I introduce the norm as sigma 1 upon 2i mod xi over say 1 plus mod xi, then this is not a norm.
Sir, this is not a norm.
So
we cannot define. Sir, this will be only a metric.
Metric only.
These types of metric space cannot be converted as a norm space.
Norm. So once it is not a norm space, that's though it is a vector space.
No,
so that's why it's not necessary.
I was saying that if we can able to define a norm, then
if you are able to define the norm, then it will follow. You have to establish also. Okay. That's fine. Okay. So this is what now another results which is also in testing. Unitary operator, for the unitary operator, let the operator u from H to H and V from H to H be unitary operator. Unitary means they are 1 1 on 2 and u star is equal to u inverse. Unitary. Okay. Here H is a Hilbert space. Hilbert space. Then the following property holds. Then U is isometric. That is norm of Ux equal to norm of x for all x belongs to H. V isometric, they are having the same norms. Okay, and norm of U equal to 1 provided H is not equal to null vector. C U inverse equal to equal to U star. U star is unitary, which is equal to U star is unitary, and UV is unitary. U is normal, and finally we get the last one, that is a bounded linear operator T E F1 F, a bounded linear operator T on a complex Hilbert space H is unitary if and only if T is isometric and surjective. Surjective means onto. Okay, so let's see the proof. Proofs are simple. So what the first U and V both are giving to be unitary. So it is given U star is equal to U inverse, V star is equal to V inverse. Then H is a Hilbert space, fine. Then we have to show U is isometric. Isometric means the norm of Ux and norm X will be the same. Okay, the U does not transfer the distances, maintain the distances. Okay, between X and Y the distance and the corresponding image will have the same distance. So to prove the part A, consider Ux norm square. This can be written as Ux comma Ux in terms of inner product, but this will be equal to X comma U star Ux, but U star is equal to U inverse. So this will be equal to X U inverse Ux, which is equal to Xx, and this is true for all X. So this shows this is equal to norm X square. Hence, follows B U in norm of U is 1. It follows from here, follows from A. Why? If I divide by this norm Ux by norm X, take the supremum over all X belonging to H, X is norm of X is 1, then it is 1. Okay, follows from here, nothing to, provided x is non-zero, normal, otherwise it will not. Okay. That's why h is different from 0. Then u inverse is unitary. To show u inverse is unitary, so what we have wanted to show first is clearly u inverse is bijective. Why? Because u is bijective, because this is given and u and v are bijective, is it not by definition? So if u is 1 1 on 2, the inverse will exist and inverse will also be 1 1 on 2. So it is a bijective mapping. Okay. Then next is, if I prove that u inverse star is equal to u inverse, then our result is okay. So consider u inverse star, but u inverse is equal to what? U star star, because u is giving to be unitary, so u inverse is equal to u star. So u star star is u, that can be written as u inverse inverse. Therefore u inverse star is equal to u inverse inverse, so u inverse is unitary. Is it okay? Clear? U inverse is bijective as well as u inverse star becomes the u inverse inverse, because this is a u star equal to u inverse now. So that's all. So this follows. Then next is uv is unitary. uv is 1 1 on 2 follows, because u is 1 1 on 2, v is 1 1 on 2, the product will be 1 1 on 2. And now consider uv star. This is by definition v star u star. V star is equal to v inverse, u star is equal to u inverse, but by definition this is uv inverse. So uv is unitary. Clear? Then u is normal. So u is normal means what is to be proved is, u is normal means u star must be u star u. So u star, u star is equal to u inverse because given. So this is I, which can be written as u inverse u, but u inverse is u star u, so u is normal. Okay. Now last one, what is needed is this: a bounded linear operator T on a complex Hilbert space is unitary if and only if T is isometric and surjective. Okay. This, so suppose T is isometric and surjective. Isometric means norm of ux equal to norm of x, and surjective means it is onto. Now what is required to prove is, required to show that T is unitary. T is so we wanted to show T is bijective and T star equal to T inverse, is it not? So T is on 2 follows from this relation. Oh, sorry, let us take u instead of this, let us take T, because T is isometric, because T is isometric, so it satisfies this norm of Tx equal to norm x. It means each point will carry to the same the length of this vector of each point under the image will be the same. Clear? And this is true for every x. So there will be a 1 1 on mapping corresponding to each x, you are getting Tx. Okay. So two different x1 and x2, their length will be different, therefore Tx1 will be different from Tx2, is it not? So the one onto ness will follows from this. Is it clear? Because okay. So, we get onto follows from, because this is given.
Sir, on
No, one sorry, oneness.
sir, T is isometric. Huh?
T is
Isometric
one. T is one follows from there. Yes.
so T is isometric. Isometric means two space. The operator is isometric means there is a isomorphism between the two space.
Isometric means that.
There is a isomorphism between the two space.
No, isomorphic, then two also isomorphic matrix. Isomorphic is a one onto mapping which preserve the operations.
Which preserves the operation.
Okay.
Means the diameter.
So whenever we go for the norm space, then it becomes the isometric.
Yeah, this is isometric.
Isometric. So length is the same.
First point is that there must be an bijective of
Okay.
bijective matrix. And there is a proof in linear algebra that if this exists, then the dimension of these two cases must be same. From that it is on.
Or otherwise oneness. You want it the oneness, na? You can say from here, suppose why, because I am writing T of x1 minus x2, I take it. Okay. T is isometric, so this will be equal to. Okay. Now if I take this is equal to 0, x1 equal to x2, tx1 equal to tx2. Okay. So if x1 is equal to x2 will implies tx1 equal to oneness. Okay. So basically T is 1. T is onto is already given in the problem. It is surjective. So T is surjective, T is injective, therefore T is bijective. Okay. 1 onto is a. Now only thing we have to show that T star T is the same as TT star. So start with this inner product T star T x comma x. Okay. Now this can be written as Tx comma Tx because of the property adjoint, but T is isometric, so this is the same as xx, and this will be equal to Ix comma x, but this implies x comma x is 0 for every x belongs to H, where H is a complex Hilbert space. This is given, H is a complex Hilbert space. So complex Hilbert space. Therefore T star must be equal to T. Therefore T star minus T is 0. So T star will be equal to T. Okay. Is it okay or not? Oh sorry, T star. This is, I am sorry, this is T star T. T star T, and this is I. We are transferring this I. So sorry. So this is T star T minus I. Okay. So T star T must be I. Okay. Now you consider T star T star. This is equal to T star, and then I we can write T inverse. This will be equal to T star T inverse, but T star T is already proved to be I. So this is equal to again I. So what we conclude is T star T is equal to T star. Hence T star will be the inverse of T, because those product and which is coming to be I. So one should be the inverse of the other, and this shows T is our T is unitary. Is it okay? Now let us see the converse part. Converse follows easily. If T is unitary, then it is isometric because of the first property, by the first result, and then second one what it says is, second what you want to do, if isometric and surjective follows, and surjective by definition, because unitary means it is bijective. So definition, by definition it follows surjectiveness, and because T is unitary in the first case you have already proved T is isometric. So that's okay. So this completes the. Okay, thank you. Clear?